calls that you can make from user space into the kernel and basically ask it to do things. And that's a very important aspect of the way the OS works. It's an interesting relationship, if you want to kind of personify it, that code running in user space, your applications, are running effectively at the lowest level of privilege that the system offers, that the CPU offers. The kernel's running, leaving aside trust zone and other aspects of hardware security, is running effectively at the highest level of privilege. Applications ask the kernel to do something, and the kernel will do its best to satisfy that request, subject to any controls that are in place and any restrictions that are in place. So if you try and open a file that you don't have permissions to view, then the kernel will say, no, you can't do that. That alone isn't enough to secure a system. Permissions is one and another fairly sort of lightweight tool in the toolbox, if you like. When you make a system call, typically via your C runtime library, that gets intercepted inside the kernel. You can see open in this example, turns into a call sysopen in the kernel, and it goes into this magic block inside the kernel called the VFS, the Virtual File System Switch, and it's this block that routes that call to the appropriate place. So if it was opening a file, it would go off into the file system handling code, open this file on a USB stick or whatever it might be. If it's actually interacting with a piece of hardware, then it would send it down to the relevant device driver. So what we're talking about when we see LibSeccomp in action is at this level, between user space and the kernel. The second sort of concept that we want to get a handle on is the way that new user space processes are created. And that's done with quite a simple relationship between a parent process, and the new process is referred to as the child process, parent and child. Every time on a Linux system you type a command into the shell, you may well be users of Linux or maybe even going further back, Unix, you type ls, it lists out the files in that directory. In that context, the shell is the parent, and the ls command, the ls program, is the child. And that parent has created that child. And it does that with a call to a special function called fork, which is one that has to be pronounced very, very carefully when doing presentations like this. Particularly when you start talking about forking a child, it can get very messy very, very quickly. So the key point here is that the second process inherits most of the state from the first. So it's effectively a copy. It's not quite as simple as that, but it's effectively a copy. And then there's a family of calls that are then can be executed in the child process that will load the new program, the ls binary. They're called the exec family. There's sort of variants on those. Can choose how to load that new binary in different ways. We can see, if I move out of the way, there's a tool called strace that will let you trace system calls that applications make. And if you strace ls, for example, the first line is execve. It shows us that the first thing that's been done is that the binary user bin ls has been loaded into that child process. So we have system calls, which is how user space and the kernel interact, and we have the concept of a parent and a child process. What the LibSeccomp feature allows us to do is filter the system calls that are made by a process. So some places I say LibSeccomp, and some I've been saying LibSeccomp. LibSeccomp is the kernel feature that allows us to do this. So it's part of the mainline kernel. It can be enabled very simply with a simple configuration switch compiled into your Linux kernel. LibSeccomp is a user space library that provides APIs and tools that help us configure this. And what it allows us to do is, in a parent process, to set up a set of filters to control what system calls are allowed. And then we can, from there, launch a child process which is subject to those filters without even knowing it. And if that child process tries to do something that it's not allowed to do, the kernel, no interaction from user space at all, the kernel we'll terminate that process. We'll stop it in its tracks. It's no longer running within the system. So if we're running our processes, particularly if we have untrustworthy processes, maybe open source programs that we're not 100% sure about, for example, or processes running very sensitive data that we want to maybe design to a worst case scenario. If somebody's going to attack our system, this is the process they're going to attack. We can run them in a way that restricts what they can do. And we can limit those 300 plus system calls. It's maybe kind of interesting that by default, you can do anything in a system. That's maybe counter to secure design right at the outset. So the LibSeccomp functionality allows us to control what each process can do. In terms of building it, those of you familiar with working with Linux in embedded systems are probably familiar with the Yocto project. It's easy to build it into your system is the message there, really. The kernel feature uses something called BPF, Berkeley Packet Filtering, which is a feature of the kernel used in all sorts of crazy things. We're not going to get into that. It's beyond my knowledge base, frankly. We've got a nice, friendly user space library that does all the work for us. So if we look at a code snippet, I dare say this is the only presentation here today with snippets of C code in it, and I see that as a good thing. We can see this is the parent process that's going to launch the child. And we basically initialize the LibSeccomp filtering, and we set an action. Here it's set to kill. There are other things you can put in there like log, as we'll see. And then we're effectively putting pinholes of what's allowed. We're adding rules, each set to allow in this example, with the name of a system call. We're going to allow reads, writes, and closes in this instance. The 0 at the end here hides a great deal of complexity. You can actually set the parameters that you're going to allow as well. There's a set of quite complicated macros you can use to put, I will allow you to read from a file, but only in this location on the file system, or something like that. So you can really go very detailed in the way that you're setting up these pinholes, as I say. The final stage is to load the filter, represented by a data structure, into the kernel. It's then running, it's active. An open question is, how do you know what system calls you need to allow? What do you need to make sure that your application can do, but for its normal operation to carry on, but what things are not allowed as well. And so one way to do that is actually to set the action to log, run your application, run your test suite, try all the different code paths, all the different potential inputs, and then in the system log, the standard Linux system log, you get a listing of all of the different system calls that have been made. There are other ways you could derive that information. And they're all given a number. That, in and of itself, isn't enough because these numbers vary by the architecture family that you're working with, which is why you may have noticed here, that's hidden behind a macro so that we can write portable code as well. The library provides a nice tool, a resolving tool. You tell it what architecture you're working with here, ARM64. You give it the number, and it gives you the system call. So you can build up a list of what you want your application to be able to do, and that obviously implies there's a whole other list of things that you don't want it to be able to do as well. So in the controlling application, in this simple example, obviously include the headers, we've seen the initialization and rules. Here we're just calling fork to load a child process. The child process itself is completely unaware of what's going on. It's playing a game without knowing that it's playing a game, and it could be, without wishing to be too brutal, it could be killed at any point if it breaks the rules of that game. It's like some sort of sci-fi story. That means we can use it even with binary-only objects. If we don't have the source code, it doesn't matter. As long as we're loading that binary, we can deal with that. So that's doing a kind of homebrew setup. In a production system, you may do that, but you're less likely to do it. What we're going to typically do is use this system call filtering in conjunction with other mechanisms as part of a fully featured and secure Linux system. Maybe starting on this side. So there's a process in user space called the init process with process ID 1. It started by the kernel on boot. It's the ultimate parent or grandparent or great-grandparent of every other process in the system. A useful tool if you're in Linux called pstree can help you visualize that. So that will start all the other services that you have running in your system. Most modern systems use an init called systemd. It's what desktop almost always uses, and it's becoming more common in embedded systems. And it has a mechanism for setting up system call filtering per process. So as part of the initialization, the bring up of your system, filtering is put in place. You could use that, or you could use system call filtering directly in some sort of isolated execution environment, which is what we can see over here. And this is something, it's coming from the world of cloud and all the Kubernetes and all that sort of stuff. But again, we're seeing it used more and more in embedded systems where processes or groups of processes are run in an isolated execution environment using a mechanism like Docker or LXC underneath. And these things can also configure system call filtering. So even where our container contains a single process just doing its thing, that has a limit on what it can do and what it can ask the kernel to do. And so even if that single potentially untrustworthy process is compromised in some way, it is stopped in its tracks and is not allowed to do anything more. So this is a powerful mechanism. It's one important tool in the toolbox that we have for protecting a system from some sort of compromised process that's either been attacked at rest, somebody's got onto the storage, or it's been attacked with a live attack, via some known vulnerability, the sort of coding mistakes and things that people make very commonly, unfortunately. But it's only one very small part of securing the embedded Linux system. We wanted to pick an example of the sort of thing you can do with Linux to secure the system. And this rather busy picture just shows us in different areas all the different things that you could think about in terms of securing the embedded Linux system, from file system integrity checking and encryption, secure boot. We can see LibSeccomp here as part of the OS features alongside permissions and mandatory access control and other things. There's network security mechanisms. There's different languages we can use. We've been using C here, but it's interesting. I was at the Open Source Summit a couple of weeks ago, and one of the announcements was that support for the Rust programming language is coming very soon into the kernel. So you can write device drivers in a memory-safe language. That's going to be an interesting step forward. So all of these things can allow us to satisfy the requirements of a framework like the IoT Security Assurance Framework in a very complex and rich environment. Okay, thank you. Happy to answer questions, or if you want to speak to us offline, we have a tabletop out there. Thank you.